embedded something like this inside the, right? So you have 1, 2, 3, 4 edges touching N-type source, touching P-type body, and then you have the bottom surface also touching. Top surface of the source is open to the terminals, so there is no p-n junction. So if you look at the source diffusion submerged inside the body, p-n junctions are formed along the sidewalls, and the bottom surface. So there are 4 sidewalls. However, on the channel side, when the transistor is on, we are talking about NMOS transistor, an N-type channel will be there from source to N, source to drain. So that side of the sidewall is covered by the channel. Source is N-type, drain is N-type, channel is N-type. So you have a continuous N-type path. So when the transistor is on, there is no p-n junction between that sidewall and the body. So if we look at it, this sidewall, this sidewall, this sidewall, and this sidewall, 4 sidewalls and the bottom surface will be contributing to the p-n junction. But when the channel is present, this sidewall is covered by N-type channel, so there will be no p-n junction capacitance contribution from this sidewall. So the total will be then 3 sidewalls, 1, 2, 3, and 1 bottom surface. So now, so the total diffusion capacitance that we will get from each source body p-n junction will be contribution from the bottom surface and the sidewall contribution. Typically, for this bottom surface, a per unit area capacitance will be given in the technology data sheet. So you multiply this source area. Source area will be length of the source times width of the source. Width of the source is exactly equal to width of the device. So length of the source Ls times W, that is the area of the bottom surface, times Cj, per unit area capacitance, p-n junction capacitance, that will be determined by the technology, the doping density and material. So that is the contribution. And CJSW, there is per unit length capacitance. Another technology data, per unit length p-n junction capacitance along the sidewall. So the per unit length times total perimeter, that is contributing the sidewall p-n junction capacitance. That will be one LS, 2 LS, 1 W. This side we are not adding because it is covered by the channel. So that will be then CJSW, sidewall per unit length capacitance time 2 LS plus W. So that's basically how to estimate the p-n junction capacitance. So just as I said, this is just an estimation. You cannot 100% accurately calculate this capacitance. This is an equation I want you to just know. You don't have to derive it because this is part of the basic semiconductor solid state device class. But we will take this equation as it is. How threshold voltage of a transistor is dependent on different parameters of the device. Threshold voltage of a transistor Vt is equal to Vt naught plus gamma is called body effect coefficient. It is a constant for a certain technology. Root over pi f plus BSB. So this whole here, how many terms we have? Gamma is a constant. Pi f is called Fermi potential. It is a material property for a particular device, for a particular material. VSB is the effective voltage between source and the body terminal. Earlier we explained that source and body of MOSFET transistors are connected together. To maintain zero body bias, zero bias between source and the body terminal. They're connected together and together with ground for NMOS, together with VDD for PMOS, to maintain zero effective voltage between source and body terminal, so that PN junction is not biased, so that you don't have a leakage downward. However, in actual circuit, source is always active. Something is entering through the source and leaving the device through the drain, right? On the other hand, body is a reference terminal, permanently connected to the ground. Although source is also connected to the ground in case of NMOS, the source terminal is an active terminal. So temporarily, oh, someone is there. Next time, $5 for every 5 minutes. So, during the operation, because source is continuously active, although it is connected to ground, but temporarily, because of the continuous flow of current in and out of the source and the drain, temporarily, source body potential, source terminal voltage will go above or below the reference. As a consequence, temporarily, a voltage difference will appear between source and the body, although they are connected to the ground or supplied together. Because body is an idle terminal, reference terminal, but the source is an active terminal. Because of this, during the operation of the transistor, temporarily an effective voltage difference, source to body voltage, will appear. Sometimes it can be negative, sometimes it can be positive. Depending on the magnitude of VSB, the source body effective voltage, the threshold voltage can be greater than VT0 or less than VT0. VT0 is the threshold voltage when this effective voltage difference is actually zero. So this is the ideal threshold voltage when source and body is truly at the same potential. So between them there is no voltage difference, no bias. But practically, now if you put VSB equal to 0 here, this cancels this, VT becomes equal to VT0, right? That is the ideal threshold voltage. So, but in real life circuit, during the operation, under any circumstances, you cannot keep this exactly at 0. Sometimes it will be a positive value, sometimes it will be a negative value. So we are, if needed, we are going to use this equation to calculate actual voltage behavior. But this shows you how threshold voltage will be changing during the operation time due to the appearance of source body voltage. In advanced VLSI design and mixed signal IC design class, we will see that how this difference can be intentionally modified, made it positive or negative to control certain noise. But let's not talk about it. With that, we covered all the basics of MOSFET device. As I have been repeating, please spend a lot of time on this lecture 2, because everything else you are going to learn in the subsequent lecture will be meaningless. It will be very difficult for you if you do not understand the topics of lecture 2. So now that we covered MOSFET device, now we are going to form circuits using MOSFET device, and we are going to talk about CMOS logic circuit. in this lecture. The basics of CMOS logic circuit. So if you understand the content of lecture 2 and 3 very well, then you can actually answer most of the 90% of the interview questions in logic circuit. So this one slide I'm going to repeat almost at the beginning of every lecture for the next 3-4 set of lectures. You need to understand the classification of digital logic very clearly. Digital logic circuits can be classified from many different angles, based on many different characteristics or properties. One of the most important criteria to classify digital logics into different class or group is the input-output relation. How output is determined for a given set of input. That relation, input-output relation, is one of the most important criteria or property to classify digital logic circuit. Based on input-output relation, digital logic circuits are divided into two groups or two classes. One is called combinational logic, the other one is called sequential logic. We are going to define one by one. And then each of these logic types, combinational or sequential, can be implemented by two different types of logic. One is called static logic, the other one is called dynamic logic. So, a combinational logic circuit can be implemented based on a static logic style or dynamic logic style. A sequential logic circuit can be implemented based on static logic style or dynamic logic style. So based on logic style, how output signal is retained at the output node, based on that, the logic values are determined at the output node. Based on that, it can be of two styles, static and dynamic. And then, there are many different circuit design techniques that can be used to implement any of those combinational, sequential, static or dynamic logic circuits. So this group of classification is basically based on implementation techniques or circuit design techniques, logic circuit design techniques. The first and the most important one, the most dominant one, is the CMOS logic circuit. And then there is another group of logic circuit called ratioed logic circuit. If you put it in Microsoft Word, this is an incorrect word grammatically, but in digital logic circuit, this word has been used from the beginning. So there is one group called ratio-less logic. The other one group is called ratioed logic circuit. We will explain it later. And then a special class of ratioed logic subclass is called differential cascade voltage logic circuit. And the third type of logic circuit is called pass transistor logic circuit. And a special class of pass transistor logic is, I should have put it in the one step to the right. Because this is a special case of ratioed logic, this is a special case of pass transistor logic. So basically, there are three major logic circuit design techniques or implementation techniques: CMOS, ratioed logic, and pass transistor logic. Differentiate, and there are many different subclasses of ratioed logic, and one unique and special case of ratioed logic is DC-VSL, and the third type of logic circuit technique is called pass transistor logic circuit, and one special case of pass transistor logic circuit is transmission gate based logic circuit. So we are going to repeat this slide, lecture 3, lecture 4, lecture 5. Now let us define the first one, input-output relation-based classification. Somehow the format is messed. Anyway, don't worry, I will upload the PDF format. It's called, actually it's written CMOS logic, a combinational logic. Somehow the word is okay.
But the hair is fine.
It is fine, but this computer is acting
I think
weird.
you can download the PDF and then present
Yeah.
it.
Yeah.
But it is not allowing me to download because it says this computer, there is no storage right now.
Oh.
I don't want to delete any other faculty members' stuff from here. Okay. So, there are some logic circuits where the output signal will be determined by the input signal applied at that moment. So the input signal you are applying at a particular time instant, they will determine the output of that time instant. Output will not depend on what happened before. There is no memory effect. The current inputs will determine the current output. So the output is the function of the current input. So combination of the current input will determine the current output. That logic circuit is called combinational logic circuit. However, in some logic circuit, what happened previously, some of the signal, some of the information will be stored in a memory block called state preservation block. Whatever input you apply currently at a time instant, plus whatever is stored in that state preservation block or memory block from prior operation, together will determine current output. So the current output will be a function of the current input plus what happened before. So the sequence of the signals you applied will determine, because there is a memory effect, will determine your current output. That's why it is called sequential circuit, also known as regenerative circuit, because it generates output based on what happened before, not only the current input. So combinational or non-regenerative circuit is the one where output is the function of only the current input. Sequential or regenerative logic circuit is the one where output is the function of the current input and previous input. So, the difference structurally and functionally, the difference between a combinational and sequential circuit is the presence and participation of a memory block in determining the output. So, constructionally, a sequential circuit is nothing but a combinational circuit plus a memory block. That memory block will collect its input from the output and feed it back to the input. So it's in a feedback loop. So a sequential circuit is nothing but a combinational circuit block plus a memory unit in a positive feedback loop. Why is it called positive feedback loop? Because you are adding output back to the input. Now let us look at the second classification based on the logic style. There are two types of logic. One is static logic, there is a dynamic logic. In a static logic circuit, there will be two distinct blocks of, we will talk about the details, so don't worry about all the details here. In static logic circuit, there will be two distinct blocks of transistor. One block of transistor will constitute what is called PDN, pull down network. Its job is to connect output to the ground to produce binary low or zero value. So it will be constructed of NMOS because NMOS will be pulling down. There will be another complementary block of transistor that will constitute pull-up network. Its job is to connect output to the supply to produce binary 1 or high value, and it will be constructed by PMOS transistor only because PMOS is good at pull-up, very good at, is a pull-up device. The number of transistor, NMOS transistor in pull-down network will exactly equal to the number of PMOS transistor in the pull-up network. So if, and that number will be equal to the number of input. So if you are given the task to design a 5-input NAND gate, you need 5 transistor in the pull-down network, you will need 5 transistor in the pull-up network because each transistor can take maximum 1 input. So for 5-input NAND gate, you need 5 transistor here, 5 transistor here. The total number of transistor will be 5 plus 5, 10. So the number of transistor you need to implement any static logic circuit will be equal to twice n, where n is the number of inputs, small n. So we need small n number of n-type MOSFET, small n number of p-type MOSFET in pull down and pull up block. That is the basic construction and function of a static logic circuit. This network, pull down network, is responsible for producing binary 0 or low. This pull up network is responsible for producing binary 1 or high. It will be made of NMOS, it will be made of PMOS, and they are complementary to each other in terms of function. One is responsible for 0, the other one is responsible for 1. They are complementary in terms of the types of transistor used to build them, NMOS and PMOS. On the other hand, later we will see that we can actually simplify this logic circuit and implement the same logic function with only pull down network or only pull up network. If we can implement the same logic function, 5-input NAND gate, with a pull down network only plus 2 clock transistor, or pull up network only plus 2 clock transistor, this type of circuit or logic style is called dynamic logic circuit. Why it is called dynamic logic circuit? We will talk about it later. Let's not talk. That will be lecture number 5 or 6. But in dynamic logic circuit, what do we see? This pull down network will be exactly same as this pull down network. So for a 5-input NAND gate, if I need 5 NMOS transistor here, I will be needing 5 NMOS transistor here. So the total number of transistor to implement a dynamic logic gate for a particular function will be n plus 2. So for a 10-input logic function, you need 10 plus 10, 20 transistor here. You need 10 plus 2, 12 transistor here. So as the logic function becomes larger and larger, it is beneficial to implement it using dynamic logic style, because then you need almost 50% resources. For a 20-input logic gate, you need 40 here, you need 22 here. Why you need 22 here, why you need 40 here, we'll explain that later. But in terms of immediate benefit that we can see, the number of transistor is twice n to implement the logic function in static logic style. Same logic function, if you implement in dynamic logic style, you need n plus 2 transistors. Okay. Now, I am just here showing one version of dynamic logic circuit. There can be another version of dynamic where it will only have pull-up network plus 2 clock transistor. Why it is called static and why it is called dynamic and how it works, we will explain in the subsequent. Static one we will explain in the rest of this lecture, but dynamic one we will wait for lecture 5. Now let us talk about static circuit. We are in this lecture we are going to talk about CMOS static circuit. So let us go back. In terms of input-output relation, circuit can be combinational type or sequential type. In terms of logic style, it can be static or dynamic. And in terms of circuit implementation techniques, it can be any of this type. In this lecture, we are focusing on combinational circuit, static type, implemented using CMOS technique. So this lecture is about complementary CMOS logic, static combinational CMOS logic. And we are going to explain the operation and design techniques of static combinational CMOS logic circuit using a simple inverter as an example. So here, from the title of the lecture to this slide, we are talking about combinational logic circuit but static type. And we will be only focusing in this lecture on this circuit technique. So we're talking about CMOS static combinational logic circuit in the rest of this lecture. So now, a CMOS static circuit is made of two circuit blocks or two networks. One is called pull-down network, the other one is called pull-up network. One of the fundamental requirements for a CMOS logic circuit, static logic circuit, to work as a logic circuit is that we have to make sure that for a given set of input, only one of them is turned on. That means the output, if this one is turned on, output will have a connection to ground. If that one is turned on, output will have a connection to supply. For output to be binary 0, you need a connection to ground. For output to be binary 1, you need a connection to supply. If both networks are simultaneously on, output is connected to ground and supply, so output node will be confused. So your output signal will be in undefined region. It will be an erroneous value. You can only have, it's a binary logic, you can only have one of the two possible states, low or high, right? Binary 0 or 1. You cannot have both. Then it will not be a logic circuit anymore. So that's why output in the steady state can only have either connection to ground to maintain binary 0 or have a connection to supply to have a binary 1. So for a given set of inputs, same inputs are going to pull-up network and pull-up network. If same set of input cannot turn on both network. For a given input, if you see that your pull-up network and pull-down network both are on, that means your circuit design is incorrect. So that is the first and the most important requirement to design. The way you have to arrange the transistor for a given set of input or a single input, only the pull-up network or the pull-down network should be on, not both. And if we do that, let's say for a given set of input, pull-down network is on, pull-up network must be off, so the output will have a connection to ground. So output's ability to maintain and produce and maintain binary 0 or low will be helped by having a steady state connection to the ground. So a noise or any kind of disturbance cannot distort the value because it will have a steady state static connection to the ground as long as the pull-down network is on. Similarly, when a given input turns on the pull-up network, this must be off. Output will maintain a 1 or binary high by having a connection from output to VDD, and that output will be strongly 1 because it is having a steady state static connection to supply. So in static logic circuit, output value will be maintained by having a static connection to, continuous connection to ground or supply. So it will be very robust and strong output signal. So we have to, that's why it is called static logic circuit. So in static logic circuit, output node will maintain its output state by having a connection to ground or connection to supply. That's why it's called static circuit. Now, in static combinational logic circuit, CMOS static logic circuit, the pull-down network is made of NMOS transistor, pull-up network is made of PMOS transistor. Why? Because it's a complementary. That also guarantees that for a given set of input, both network will not be on. Why? For NMOS transistor to turn on, you need high signal at the gate. For PMOS transistor to turn on, you need low signal at the gate. So input signals will be always applied for CMOS logic circuit to the gate terminals. So the input signals in a CMOS logic circuit, I'll give you lots of information, will be applied to the gate terminals. And we know that for NMOS to turn on, you need to apply high input at the gate. VGS should be supplied. For PMOS to turn on, you need to apply a low signal or ground signal at the gate. So if the input is high or the set of inputs are high, it will turn on the NMOS transistor, not the PMOS transistor, and vice versa. So that way, it guarantees that the complementary nature of types of transistor guarantees that for a given input, only one of them will be on, and output will be connected to ground or supply depending on the input value and depending on which of these two network is on. So another thing to observe here, when input is high, pull down network will be on because NMOS transistor will be on when inputs are high because inputs are connected to the gate. If input is high, pull down network will be on. In that case, output will be connected to ground, that is output will be low. So for high input, you are getting low output. If the input is low, pull up network will be on, output will be connected to supply, it will be high. For low input, output will be high. So that's why this CMOS circuit is known as inverting logic circuit. For high input, it produces low output. For low output, it produces high output. Later we will see that these two networks, they are not only complementary in terms of function and transistor, they are also complementary in terms of connections. Let's say inside this pull-down network, if it is a 5-input logic circuit, you will have 5 NMOS transistors. Those 5 NMOS transistors will be connected in some sort of series parallel combination depending on what type of logic circuit you are implementing. If the NMOS, 2 NMOS for signal A and B, let's say A and B, they are connected in series here, they will be connected in parallel here. If they are connected in parallel here, they will be connected in series here. So, pull down block and pull up block, they are complementary in terms of their role or function. One is responsible for 0, one is responsible for 1. They are complementary in terms of the types of transistor, NMOS and PMOS. They are also complementary in terms of their internal connection. A series connection will become parallel over there, a parallel connection in the downside will become series connection in the pull-up side. So they are complementary in every possible aspect, and we already explained why. Pull-down network is made of NMOS because it's a good pull-down device, while pull-up network is made of PMOS because it's a good pull-up device. So working principle we already explained. For a given set of input, if pull-down network is on, output is connected to ground, we get binary low at the output. If input is high, input is low, pull-up network is on, output is connected to supply, and we get output basically high. For low input, output high. For high input, output low. So that's the way it functions. That's why it is called inverting logic circuit.
So at one time we will be getting two outputs. One for at one time if we are giving one input, they are getting two output voltages.
Yeah.
right?
So any logic circuit can have only two possible outputs, either binary 1 or binary 0. So that's why it's called binary circuit. Only two possible states. Anything in between will be metastable. It will be either fall into 0 or fall into 1. So now, if we want to summarize, what are the key defining characteristics or properties of CMOS logic circuit that made it the most popular logic circuit for IC application? Number one, it is able to produce perfect logic 0 and perfect logic 1 because the pull-down network is made of NMOS, pull-up network is made of PMOS. And it has very high noise margin and noise tolerance. Why? The output maintains 0 by having a steady state connection to ground. Output maintains binary high by having a steady state connected to supply. So any temporary noise injection can be quickly neutralized or discharged or charged by having a connection to ground or supply. So compared to any other logic circuit, due to the steady state connection of the output to the ground or to the supply, its noise margin is very high. The third most important characteristics of CMOS logic circuit is ideally it consumes 0 power during the steady state operation. Why? When you have a steady state 0 here, this is on, this is off. Supply is disconnected from the ground, so nothing is flowing through the circuit. When you have a steady state 1 here across this capacitance, this is off, this is on. So this again supply is disconnected from the ground. So at steady state 0 and steady state 1, supply is disconnected from ground. Ideally, there is no current flowing when you are maintaining a steady state 0 and steady state 1. So ideally it consumes 0 power in steady state condition. So, but practically there will be some leakage and transition power. So that is something. These are the 3 major benefits that make CMOS the dominant circuit design style for any IC. Perfect logic level, very high noise margin, ideally 0 power consumption in steady state. However, when you are turning on this pull-down network, output, if initially high, it does not discharge or become 0 instantaneously. There will be some finite time for the output to be discharged to the ground and get the perfect 0. Why? Because this pull-down network, this wire, these are made of physical wire, physical transistors, which will have resistance, capacitance, inductance, lots of parasitics. So even if you turn on the pull-down network, output will not go down to 0 instantaneously. It will take some time before it reaches its steady state. And when pull-down network is on, pull-up network is not turned off like instantaneously. As pull-down network is going to stop on state, pull-up network will gradually go down and become off. So there is a transition period, one going up, the other is going down, right? Before each one of them reaches final destination, before this one is completely turned off, it will keep injecting a current here, it will keep discharging this voltage here. So when it will go down, when this current is larger than this. When this voltage is completely discharged, this will become 0, this will become 0, because it is 0, no more current. So until it reaches the final state, there will be current activity here and here. If it is discharging, this one will be larger than this one. If it is charging, this one will be larger than this one. So during the transition state, when the currents are not equal, one is larger than the other, during that time slowly it is going up or slowly it is going down. That is called the transient behavior or dynamic behavior. During the time when this current through pull-up network and pull-down network will not be equal to each other. However, when they reach their final destination, both current will become equal to 0, ideally, but practically there will be some leakage. But it will be equal leakage so that it maintains at 0 or 1. So steady state or static behavior will be when both currents are equal, ideally equal to 0. So here, do not confuse with the term dynamic and static here. Here we are talking about the behavior of a logic circuit. Its behavior when it reaches the final values at the output is called static or steady state behavior. During the transition, when it is making an upward or downward transition, the behavior during that time is called dynamic behavior or transient behavior. So, a static circuit can have static behavior and dynamic behavior. A dynamic circuit can also have static behavior and dynamic behavior. So do not confuse with those two terms. Static behavior is the behavior of the circuit when it reaches its final value, no longer signal transition taking place. Dynamic behavior is the behavior of the circuit during the transition, going upward or downward. Any electrical circuit or electronic circuit will have static behavior and dynamic behavior. Don't confuse it with the logic style classification. Due to the shortage of words in English, they are using same terminology to actually explain different things. Okay. So now let us introduce a basic inverter, because in the rest of the lecture we are going to talk about or analyze the behavior and operation of CMOS static combinational logic circuit using an inverter as an example. Because inverter is the simplest possible logic circuit you can have, and everything we discuss in terms of inverter will be true for any complex static CMOS logic circuit. So what is an inverter? Let's start with the basic definition. An inverter is the simplest possible logic circuit that has a single input and single output. If you apply a high input, it will produce a low output. If you apply a low input, it will produce a high output. And this is the truth table, if A and B are the inputs and outputs. So inverter from electrical point of view, what is this? It is actually two voltages at the input and the output. And the level of voltage will determine whether it's a logic 0 or logic 1. So the way inverter is designed, like CMOS technique, if I apply a high voltage, it connects the output to the ground, so thereby getting a 0 voltage level representing binary 0. If I apply a low input, this output will be connected to supply. Output will get a high voltage, supply voltage representing binary 1. So that is the basic definition of a CMOS static inverter. Now, first we are going to talk about the ideal IV characteristics, current voltage characteristics of a CMOS inverter, and later we will see why CMOS circuit has become so popular? Because we will see that CMOS logic circuit can give us a behavior very close to the ideal one. First, and all other logic circuit, their behavior will be significantly deviated from, distorted from ideal behavior. But first let us define what is the ideal behavior of an inverter. We are talking about voltage transfer characteristics. Now let us define voltage transfer characteristics. Any graphical relation between input and output voltage is called voltage transfer characteristics, VTC. Not only for logic circuit, for any electrical or electronic circuit, the graphical relation or the mathematical relation between input voltage and the output voltage is called voltage transfer characteristics. So, it's a relation in XY plane between input voltage and the output voltage. So now, we are talking about binary logic circuit. So the input voltage, what is the maximum range? From 0 to supply, 0 to VDD. Output voltage, what is the maximum possible range? 0 to VDD. Now, for a low input, output should be high. For high input, output should be low. So in an ideal inverter, from 0 input, as we are increasing up to half VDD, up to 50% of VDD, the inverter will consider it as 0 input and corresponding output will be high. For upper half of the input signal, half VDD to VDD, input will be considered as high input, corresponding output will be 0. Logic output 0. And the transition from logic output 1 to logic output 0 will happen exactly at half VDD. Input equal to half VDD. From this direction or from this direction. So ideally, there is no loss in this signal, in this inverter. For half of the input range, first half, the inverter will consider it as low input, so it will produce a perfect high output. And for the next half of the input signal, it will consider it as a high input, so it will produce a perfect grounded output value. So it will be perfect 0 logic, it will be perfect 1 logic. And the transition from 0 to 1 or 1 to 0 at the output will take place instantaneously in 0 time at half VDD. That means we are not losing anything in the input voltage range. Half of it is valid 0, half of it is valid 1 input, and correspondingly we are getting perfect high for half of the input signal, perfect low output for half of the input signal. This is the ideal voltage transfer characteristics for an inverter or for any static CMOS logic circuit. So if we can have a behavior closer to ideal behavior, then it's a very good logic circuit. CMOS, among all the different logic circuit techniques, CMOS is the only circuit technique that can provide a behavior close to the ideal. Everything else will be significantly more distorted compared to the ideal. So we have to start with the reference, the ideal one. We have to compare it. Now, let us look at an actual circuit implementation of a CMOS inverter. Let us go back to this one, or any of this. So earlier we mentioned that the number of transistors in pull down network and pull up network will be equal to each other, and that number n will be equal to the number of inputs. In an inverter is a single input, single output logic circuit. So in an inverter, single input, so the number of pull down transistor will be 1 and it will be NMOS. Number of pull up transistor will be 1 and it will be PMOS. So if we remove this rectangular box and want to implement the actual transistor level circuit for a CMOS inverter, it will look like this. A single input going in instead of set of input, connected to NMOS in the pull down network, connected to a PMOS in the pull up network. One side of this NMOS is grounded, other side is connected to supply. One side of this PMOS is connected to output, the other is connected to supply. So now, if the input is high, NMOS is on, it will appear like a short path between supply to ground with a finite resistance coming from the channel resistance of this NMOS. And PMOS will be off, so I can consider it as an open switch. Transistor is a switch. If input is 0, pull down network, that NMOS will be off, it's an open switch. PMOS will be on and will appear as a finite resistance between supply to output, which is the channel resistance of PMOS. So this is called switch delay model or switch delay diagram of a CMOS inverter. Here I am showing it's a closed switch, it's an open switch. For input equal to high, input equal to low, this is an open switch, that is a closed switch. This is the switch delay model. From this switch delay model, we are going to know some of the very important characteristics of CMOS inverter or CMOS logic circuit. What are those? First of all, let us draw this diagram in more detail. So when your output is making a low to high transition, when your output will be making a low to high transition, input has to be 0, right? So this one will be off, PMOS will be on, it will be charged, so the output will move from low to high. When output is making a high to low transition, input has to be high, so that it is on, that is off, it will be discharged, it will make a high to low transition, ultimately it will become low. Final destination will be low here, final destination will be high here. Now during the low to high transition and high to low transition, NMOS is out of the picture because it is off. So now we are talking about the dynamic behavior. How much time you need to produce a binary 1? Speed of your transistor, speed of your logic circuit. How much time you need to produce a binary 1 will be a function of what? This load capacitance and the resistance of the PMOS network, pull-up network. In case of inverter, it's a single transistor. So RP, let us use it as a general term, equivalent on resistance of the PMOS network. In case of inverter, it's a single transistor. So the speed of producing a binary 1 is a function of RP and CL. The speed of producing a binary 0 will be a function of Rn and Cl. So you, as a designer, you are given the task to achieve certain frequency. That frequency is dependent on how quickly it can switch, right? The output can switch. How quickly it can switch from 0 to 1 or 1 to 0 depends on this timing and this timing. How quickly it can make low to high transition and again high to low transition to complete one cycle, right? That cycle time is the period, 1 over cycle time is your frequency. So you as the designer, the design parameters you are going to play with will be the equivalent on resistance of the pull up and pull down network and the equivalent load capacitance. That's where technology scaling, sizing of the transistor will come into picture. What width and what technology and what sizes for the transistors and the wires you use to achieve that certain resistance and capacitance to meet your high to low, low to high transition time, because that will determine your clock cycle and frequency. Just give me a minute. I don't know why that called again. Yeah.
Sleep only 2 hours.
So, my car is in the mechanic shop, and this mechanic is calling me because one of the parts that was delivered is incorrect. So he opened the car, now he's not able to fix it. So anyway, so the parameters, now later we will see that, actually earlier we explained the resistance RP and RN, CL is common, resistance RP and RN, both will be function of the width you select. Because you cannot play with the length. Length L is the technology size. If it is 18 nanometer technology, length L is fixed. You as the designer, you can play with the width of the transistor, make it wider or make it narrower to achieve the certain RN and RP. Now, another important task you as the designer is to achieve symmetry of the behavior when it is making low to high transition and high to low transition. So you are producing through low to high transition binary 1, by high to low transition you are producing binary 0. And any design or any circuit is good circuit when it takes equal time for both transitions. It's called symmetry of operation. If one transition takes longer than other, then your circuit will be skewed. So now you as a designer, you know what to do. You have to design the circuit in a way that equivalent RP becomes equal to equivalent RN. The equivalent resistance, effective resistance of NMOS network and the PMOS network, pull-up network and pull-down network must be equal to each other so that low to high transition, high to low transition becomes equal. Otherwise, one will be longer, the other will be shorter. So now you know the answer why in any CMOS logic circuit, PMOS transistors are 2 to 3 times wider than NMOS transistor. Earlier lecture we explained that electrons have 2 to 3 times higher mobility than the holes. PMOS transistors, charge carriers are holes, they are slower. So to get an equivalent of amount of current, you have to make them wider compared to an NMOS. So that's why in any CMOS logic circuit, to get equivalent resistance or equivalent conductance, reciprocal of resistance is conductance. To get equivalent conductance or resistance, we have to make PMOS transistor larger and wider because the charge carrier through PMOS, they are 2 to 3 times slower, having lower mobility than the charge carrier in NMOS, which is the electron. So that's why in the actual CMOS circuit, you will see that the area you will be needing for pull-up network will be 2 to 3 times more than the area needed for pull-up network. So that's one of the things you will learn when you are going to implement complex logic function using CMOS circuit. If you can play with binary algebra and if your circuit comes up with more terms with inversion, that is N-type, than the P-type, then your circuit will be more efficient because P side is always larger. So we will talk about it when we are going to talk about implement complex logic circuit. But first, let us summarize this. The speed or the frequency of any logic circuit will be dependent on how much time it takes to make a low to high or high to low transition. And that time will be a function of either RPCL or RMCL. CL being common, if you want to make a symmetrical logic circuit, you have to make RP equal to RM. Then both transition will be similar. And to express the equivalent circuit model of a CMOS inverter or any CMOS logic circuit as a switch on-off switch is called switch model of CMOS inverter or CMOS logic circuit. So, because the two switches are not on simultaneously, this CMOS inverter can give us perfect logic level. That means full voltage swing. That means its logic can swing from perfect ground to perfect VDD. So let me now introduce another definition. Voltage swing is the voltage difference between binary 0 and binary 1, high and low. In case of CMOS inverter, that voltage swing is VDD minus ground, which is equal to VDD minus 0, because in case of CMOS logic circuit, CMOS inverter, up is perfect VDD, 1 is perfect VDD, 0 is perfect ground. So high minus low, binary 1 minus binary 0 is VDD minus ground voltage, is exactly VDD, so it is called full voltage swing. Other logic circuit which is non-CMOS, they will never be able to produce a full voltage swing. It will stop before VDD or it will stop before 0. The second important observation from this switch model analysis is that the design is ratio-less design. What does it mean? When you are making a low to high transition, the only thing that will determine whether you will have a high value is whether the PMOS is on or off. If the PMOS is narrower, it will have larger RP, larger resistance. The transition will be slower. But as long as the pull-up network is on, you will have a binary 1. And its size or its resistance, their relative sizes, will have no impact on your ability to produce a binary 1 here. Similarly, when it is discharging, making a high to low transition, your ability to produce a perfect logic 0 is dependent on whether it is on and off. If it is narrower, the discharge will take slower, longer time. If it is a wider, then, so what message I'm trying to give you that the relative size of PMOS and NMOS, relative resistance of NMOS and PMOS, their ratio will have no impact on their ability to produce binary output 1 and binary, so it's a ratio-less design. Yes, their relative resistance and the size will affect the time to produce 1 and time to produce 0. In that case, if they're different, the circuit will be asymmetrical. It will have two different time for binary 1 and binary 0. It will not be symmetrical, but it will act properly as a logic circuit. It will be able to produce logic 1 and logic 0 correctly, irrespective of the relative sizes or relative resistance. And that is called ratio-less design. So CMOS circuit is ratio-less, and all other circuit we will see that we have to maintain a certain size ratio, certain resistance ratio to use that logic circuit as a logic circuit. Otherwise it will not function if we do not have a specific ratio. That's why those designs are called ratio design, but any CMOS static circuit any CMOS circuit is called ratio-less design, because the relative ratios of the resistance and the sizes of the transistors in PMOS and NMOS network will have no impact on its ability to produce correct logic level. It will have impact on timing, speed, and symmetry. The third most important observation from this, I am repeating, ideally it will have zero static power consumption, because during the low to high transition, one side is off, the other side is on, no connection from supply to ground. During the high to low transition, one side is on, the other side is off, no connection. So ideally, of course, there will be leakages in any electrical circuit. So these are the three important characteristics of CMOS static inverter, but by extent for all CMOS logic circuit, static CMOS logic circuit. Another important, the fourth most important characteristics of CMOS logic inverter, static CMOS inverter or circuit is it has very high output impedance. Why? Because the input signal is applied to the gate terminal. All CMOS circuit input signals are applied to the gate terminal. No other terminal will have the input signal. So the gate terminal is insulated from the rest of the body by a layer of silicon dioxide here, the layer of silicon dioxide here. So from the input, if you look into the circuit, whether you go to the ground, you will see insulation here, you will see insulation here. That means insulated from both sides. So ideally, it will see an infinite resistance, but practically, it will see a very, very high impedance or resistance if you look into the circuit from the input terminal, because it is insulated. And the impedance you see looking into the circuit from the input terminal is called input impedance. And that impedance is very high because the input terminal is insulated from the main circuit. So what is the benefit of having low input impedance? You need very negligibly small amount of current or no current ideally to turn on the transistor. So from the same amount of signal, you can turn on many logic circuit, because each one will be asking for ideally zero, practically a very small amount of current out of the battery driving the input signal, because the impedance, the current is effective voltage, applied voltage divided by impedance. If that impedance is very high, the required input current will be very low to turn on the device. Last one, we will end here. The fifth important characteristics or property of static CMOS inverter, it will have very low output impedance, high input impedance, but low output impedance. For low to high transition, when I see from the output into the circuit, the one side is open. Between the output and the reference, what it will see? It will see a shorted on PMOS. So it will see a small resistance RP effective between supply and output. So the output current that will be coming out of the output terminal will be Vout divided by the effective impedance. That impedance is very low, so the output current will be much higher. Having a higher output current is beneficial. Why? Because from this output of a certain logic gate, you can now deliver signal to more, because now we are having more current. Why you are having more current? Because for a given output voltage, if your output impedance is lower, if it is zero, you can give infinite current. If it is lower it is, more output current you can get out of that output terminal. So having low output impedance is beneficial, because from the same signal you can get more current. However, the question is why output impedance is low? Because looking from here or here, all we see is the effective resistance of an NMOS or pull-down network or effective resistance of a PMOS or pull-up network. And that resistance is kind of a closed switch. The resistance will be significantly smaller than the insulator you see at the input. So low output impedance is beneficial, high output input impedance is beneficial, ratio-less design is beneficial because you don't have to worry about the size ratio unless you worry about the symmetry. Power consumption ideally will be zero, but practically it will be very low because there will be leakage, and this static CMOS circuit or CMOS inverter can produce perfect logic level. So these are the 5 main defining characteristics of static CMOS inverter.
One question.
Yes.
So in case of CMOS inverter, we don't need ideal logic 1 or 0 because again PMOS is wider compared to NMOS, right? So
Yes.
their resistance will also be different, right? So how are we going to achieve this ideal condition?
So why we want to make PMOS wider? Because if you want to achieve symmetry, you have to make RP equal to Rn. But typically, NMOS transistors have lower resistance for smaller size. But PMOS transistor have for the same size higher resistance. Why? Holes are slower, harder to move. So that's why if you want to make NMOS resistance equal to PMOS resistance, PMOS transistor has to be made wider if you want symmetry. If you want symmetry in low to high or high to low transition, anyway, we'll explain it again. So that's all for today. Next